Learning outcomes. After studying this module, you shall be able to analyze how various physical methods have affected the development of bioinorganic chemistry, know the advantages and limitations of the physical methods for the specific applications for molecular structure determination and characterization of electronic structures. Learn to study the electronic properties by physical techniques such as EXAFS and electron paramagnetic resonance spectroscopy. Introduction. In order to understand the nature of transition metal center in biomolecules, it is important to get knowledge about its magnetic properties and electronic states. These properties are frequently correlated with the coordination capabilities and molecular geometry of the metal center, both of which affect the reactions that occur at such a site. The magnetic and electronic phenomenon is basic need for the most spectroscopic techniques which are used to examine the chemical reactivity at metal sites in biomolecules. X-ray methods. X-rays have wavelengths that are of the order of 1 Armstrong, that is, the same order of magnitude as interatomic distances. Due to this, X-ray sources has very much importance in the determination of molecular structure. Two fundamentally different sorts of methods using X-rays are currently widely used: diffraction and absorption. X-ray diffraction. X-ray crystallography offers the most powerful structural probe of macromolecular structure, including metal coordination geometries. Small molecules structures can often be determined with uncertainties in the bond distances of the order of 0.01 to 0.001 Armstrong. The order of precision of macromolecular structures is usually less than that for small inorganic complexes. Because of high water content, protein crystals do not diffract X-rays as small crystals do. They diffract at around 50%, which is usually highly disordered. Resolution defined by Bragg's law, where theta is half the scattering angle between the incident and the diffracted X-ray beams. D equal to lambda by 2 sin theta, which is equal to 1.5418 Armstrong by 2 sin theta. This is for copper radiation. In order to assign the electron density to specific amino acid residues, it is important to know the amino acid sequence for metalloproteins. This requirement, in addition to the need for heavy atom derivatives to determine the phase angles for the thousand of measured reflections from which the maps are generated, isomorphous replacement techniques makes the method very laborious. Structure of nucleic acids can also be determined by X-ray diffraction methods, although it is difficult to obtain suitably diffracting nucleic acid single crystals. These problems not withdrawing, the final results are usually well worth the efforts, having afforded the best structural information currently available about metalloproteins and to a limited extent metal bound to nucleic acids. For the study of polycrystalline fiber of DNA, the X-ray diffraction technique is used. Its result has great significance in the discovery of double helical structure for DNA. For the study of this type, electron dense metal reagents have proven to be valuable. Fused ring organic heterocycles such as ethidium bromide bind to duplex DNA by intercalation, occupying every other interbase pair site at saturation. Direct proof of this neighbor exclusion binding model was provided by the X-ray diffraction patterns of polycrystalline DNA fibers containing intercalated palladium complex. X-ray absorption spectroscopy. The absorption of X-rays can excite the 1s, that is the k edge, or 2s, 2p, l edge electrons of an atom of element to empty localized orbitals. This phenomena, which has been known for decades, became of great utility following the availability of high intensity, tunable X-ray beams from synchrotron radiation sources. Prior to this development, the intensity of X-rays from traditional sources was not too strong to produce interpretable X-ray absorption signals. by studying the energy of X-ray absorption edge where the onset of absorption occurs, one can often determine the oxidation state of the metal ion under consideration. Transitions from inner shell to the valence shell of electrons also allows to get electronic structural information in favorable cases. Modulation of X-ray absorption energy spectrum by backscattering from neighboring atoms produce an extended X-ray absorption fine structure, which is abbreviated as EXAFS, from which details about metal coordination geometries can be extracted. The method has great utility that non-crystalline solid and even solution samples can be studied and can be applied in metalloproteins structural studies. Geometric information derived from fitting EXAFS data to a model structure can be reliable to plus minus 0.01 Armstrong as shown by comparison with single crystal X-ray diffraction of small molecule complexes investigated by both methods. An early triumph of EXAFS spectroscopy, one that afforded it great credibility among the bioinorganic chemical community, involved the iron sulfur protein rubridoxin. From the analysis of the experimental EXAFS spectrum of this protein, it was demonstrated that all the 4 iron sulfur, that is cysteine distances in rubridoxin, are equal to within plus minus 0.02 Armstrong. This result contradicted earlier single crystal X-ray diffraction work that had indicated that one FeS bond was significantly shorter, approximately 0.25 Armstrong, than the average of the 3 long ones. Subsequent refinement of the single crystal X-ray diffraction data led to a more symmetric structure consistent with the EXAFS study. EXAFS results for metallo-biopolymers tend to be most accurate for symmetric sites in which the metal ions has relatively heavy elements where the atomic number is greater than 14 within the first coordination sphere. In this respect, the rubridoxin case was nearly ideal. For less symmetric sites with several different atom types and distances in the first coordination sphere, the data can be more difficult to fit unambiguously to a model structure. Magnetic resonance methods. Magnetic resonance is a phenomena when a particle with a magnetic moment is placed in the magnetic field, gives the state that have the moment oriented in different directions with respect to the applied field have different energies. Transitions between these states may be induced by absorption of light of the appropriate frequency. The appropriate light frequencies are in the range of microwave frequencies. When particles are electrons, usually readily achievable magnetic field strengths, the method is called electron paramagnetic resonance spectroscopy. And in the case of nuclei, the most relevant frequency range is radio frequency region, and the method is known as magnetic resonance spectroscopy. Electron paramagnetic resonance spectroscopy, which is known as EPR spectroscopy, this method is ideally suited for studying many metalloproteins, including those containing copper 2, cobalt 2, iron 2, iron 3, manganese 2, manganese 3, molybdenum 5 and metal clusters such as Fe2O3 negative and Fe4S4 positive and 3 positive, and requires sample with unpaired electrons. The method can detect high spin ferric ions at concentration as low as micromolar range, and it is also very delicate technique and is used in the isolation and purification of iron containing proteins such as ferridoxins. Purity of electron transfer proteins cannot be established by the classical biochemical approach of enzymatic activity measurements, as they do not have the measurable catalytic activity. Instead, the appearance and integrated signal intensity of their EPR spectra were monitored following the usual column chromatographic purification steps. For the study of iron and copper in bioorganic chemistry, EPR techniques are used. For both iron 2 and iron 3, iron forms redox states that can exist in high and low spin forms. EPR spectroscopy readily differentiate these configurations for ferric iron. The G and the A parameters provide extra knowledge about the coordinated ligands. Vigorous EPR spectral studies of heme iron and iron sulfur clusters have been carried out, and EPR spectra have also proved to be invaluable in studying manganese 2 with I equal to 5 by 2, giving a 6-line hyperfine pattern. Polymanganese clusters involved in photosynthesis, molybdenum in nitrogenase and oxotransferases, cobalt in vitamin B12 and related complexes, and most recently nickel in the hydrogenase component of methane, generating bacteria as well as other enzymes. In addition, EPR signals are frequently encountered in organic residues adjacent to metal centers in proteins. For example, the stable tyrosyl radical in ribonucleotide reductase and in substrates such as superoxide ion. Radical intermediates generated during enzymatic reaction can also be observed on occasion by their EPR spectra. Two significant variants of the EPR method have just originated important applications in bioinorganic chemistry. One of these is electron nuclear double resonance spectroscopy (ENDOR), in which the EPR transition is saturated while a second irradiation signal is scanned across the NMR frequency range of an isotope in a complex that might cause hyperfine splitting of the EPR lines. Usually the latter cannot be directly determined. Irradiation of the samples at definite NMR frequencies causes the EPR signal to turn into unsaturated and an ENDOR signals results. A typical application is study of 17 oxygen labeled substrates such as H2O, O2 or H2O2 with EPR active metal centers such as iron porphyrins. The second method, called electron spin echo envelope modulation (EEM spectroscopy), also facilitates identification of ligand hyperfine interactions, which are sometimes called super hyperfine, to differentiate them from the hyperfine coupling with the metal nucleus that bears the unpaired spin. Here a series of 2 or sometimes 3 microwave pulses is applied to the sample in the EPR cavity, and the effect of varying the time delay between the pulses on the spin echo signal so generated is monitored. The principles are similar to those involved in NMR spin echo experiments. This imidazole NH proton of the histidine ligand coordinated to copper 2 or iron 3 where observing the effects due to deuteration provides a perfect confirmation of the spectral assignment. Another application is to identify 14 nitrogen and 15 nitrogen nuclear super hyperfine interactions. From the magnitude of super hyperfine coupling constants, the level of electron delocalization from the metal center out onto coordinated ligands can be estimated. This information may be valuable in deducing where the sites of reactivity are on bound substrate molecules. Nuclear magnetic resonance, that is NMR spectroscopy. Nuclear magnetic resonance spectroscopic methods have been very beneficial in bioinorganic chemistry, as they have in other branches of chemistry for many years. With the development of Fourier transform spectrometers that occupy 2 or more time variables, 2 or higher dimensional NMR, the relevance of NMR spectroscopy, especially for macromolecular structural studies, has improved still further. From proton to a minor level carbon 13, nitrogen 15 and phosphorus 31 NMR spectra can be obtained distance from nuclear overhauser studies and torsion angular from coupling constants, information about the 3D structures of biopolymers including bound metal ions. Indeed, NMR methods can also help to obtain the complete 3D structures of small to medium sized proteins. One emerging area of bioinorganic chemistry that has been strongly influenced by these techniques comprises of zinc binding domains from proteins that interact with nucleic acids. The structure of 6 distinct classes of such domains have now been decided by NMR spectroscopy. In all cases, the structures were determined before or contemporaneously with structure analysis of similar units by X-ray diffraction. Paramagnetic metal ions having electron spin relaxation times that are fast enough not to broaden adjoining proton resonances beyond recognition can yield shifted NMR signals that facilitate recognition of amino acid side chain ligands. This method is especially beneficial for naturally occurring iron, cobalt and copper centers. Line broadening without chemical shift changes occurs for ligands surrounding manganese 2 and GD3 and can be used to abstract distance information when these metals are replaced for diamagnetic metals such as magnesium, calcium, zinc in metalloproteins. Line broadening by the paramagnetic transition metal is also valuable for shaping the accessibility of water to the active sites of metalloenzyme. NMR methods are often quite useful for the kinetic studies. The enormously high resolution and small line widths of NMR methods, in which differences in resonance position of nuclei are often measured in fractions of a part per million, allow signal to be distinguished or line broadening to be observed for species that are interconverting on a wide variety of time scales. Summary: X-rays are extremely useful for the determination of molecular structure. Two fundamental different sorts of methods using X-rays are currently used: diffraction and absorption. X-ray diffraction is used for the structural determination of macromolecules, including metal coordination geometries. Even small molecules can often be determined with uncertainties in the bond distances of the order of 0.01 to 0.001 Armstrong. X-ray absorption spectroscopy is used to determine the oxidation state of the metal ions of interest. Details about metal coordination geometries can also be extracted using XAS. APR spectroscopy is ideally used to study metalloproteins and in the isolation and purification of iron containing proteins such as ferredoxins. NMR methods are often quite useful for the kinetic studies.